first unit on limits. So calculus is a branch in mathematics that involves this idea of a limit. And the idea of a limit is something that you can get really, really close to. For example, if I stand this distance away from the wall and I walk halfway, I get closer to the wall. If I walk halfway again, I get closer again. If I keep doing this, going half the distance, 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 I will eventually get very, very close to the wall, but I'll never get there. Because as soon as I get really close, I can only travel half the distance closer again. And that's something that's connected to what you did in grade 11. Because technically what I just did is maybe I walked 8 units first. And then I walked half the distance, 4 units, and then 2 units, and then 1 unit. And you have already done the idea of a limit in geometric sequences. That was an infinite amount of things you added. And you would say, eventually, I would get so close to the wall that I'm basically there. And we would say that this ... is equal to 16. Because eventually I would get so close. So we've done the idea of a limit already. Something that we get arbitrarily close to. Now there's 2 types of calculus. We start with differential calculus and then we go to integral calculus. Even though integral calculus was technically discovered or thought about first. So integral calculus can go all the way back to the Greeks, and Archimedes developed something he called the method of exhaustion, which was what I showed you with the blob the other day. Figuring out the area, if you make tinier and tinier squares and rectangles, you'll get closer and closer to the right area. And wherever you have a mistake, you can make it smaller there and get even closer. And if you keep getting smaller and smaller as you're adding up those areas, it gets exhausting because you keep having to do more and more math. But if you want to get closer, you can just do more. Will you ever get to the right answer? No. But will you get arbitrarily close that you can finally say, you know what? I think I'm close enough. And one of the first things another thing, in addition to areas and volumes, Archimedes was one of the first mathematicians to get really, really close to finding the value of pi. And he used a method of exhaustion for that as well. So everybody knows pi now is like 3.14 ... decimals go on forever. Okay? And pi, where pi comes from, is a relationship between the diameter of a circle and its circumference. There are pi diameters around the circumference. And what Archimedes did was he said, I want to calculate the green circumference, but I don't have any math to do that. Instead, I'm going to take this circle and divide it into 6 equal sections and make a hexagon inside, because I know how to calculate the area of that hexagon. Then he took each of the points and drew tangent lines on them, making a hexagon on the outside. And he said, I now know that the green's distance around the green is more than the hexagon inside, because that perimeter would definitely be shorter, but less than the hexagon on the outside. And so he had a parameter. He says, my answer's in between these two. And if I can make that smaller and smaller and smaller, I can get closer and closer to the actual perimeter. And Archimedes had the mathematics. This is like over 2,000 years ago. Archimedes had the mathematics to say, well, I can just cut this in half and add a new dot halfway along. And instead of doing a 6-sided shape, I'll do a 12-sided shape. And as I draw straight lines to here, can you see that the 12-sided shape on the inside is pretty close already to the green distance? You wouldn't save that much time walking on the, if you had to walk around that object, walking along the red lines wouldn't save you that much time compared to just walking on the green line. It's pretty close. That's at 12. Archimedes went to 24, he went to 48, he went to 96. Imagine drawing 96 dots around the circle, having a 96agon, that's what it's called, because once we get past hexagon, septagon, we run out of names. So you had a 96agon on the inside, 96agon on the outside. And he said, I now know that pi is in between these two numbers. And if I wanted to, I could do 182agon. No, 192agon would be the next one. And get closer and closer and closer. So this method of exhaustion was this idea of getting to a limit. Then, differential calculus. After Archimedes, this doesn't happen for another like 2,000 years. And interesting historical, okay? So, who came up with differential calculus? Newton did, and Leibniz did. Even though they're not exactly at the same time, historically we can see that they both came up with the idea independently of each other in different parts of the world. So they both are credited with discovering calculus, even though they did it slightly different times and at different places. But you have to remember, historically at this time, if you were a scientist or a mathematician, knowledge was power, and you did not share your power. So if you found out something really important, you kept it. You used it to get answers so you could amaze other people, but you did not tell them how you got your answers, because then that would be giving up your power in some ways. So, if you would look historically, there was a time where all German textbooks would say Leibniz created calculus, and all English textbooks would say Newton created calculus. And now it's sort of understood that they both independently figured it out, and we use some Leibniz notation when it's nicer, and we use some Newton notation when it's nicer. So they both gave us different things that is very helpful. And derivatives is concerned with rates of change. It's like, you know how you found the slope of a line? It's like a whole mathematics of finding slopes. Doesn't sound very amazing. It's, if you break it down, it actually sounds quite simplistic, and it is. But its ability to do things is so powerful. So it's kind of cool. And then it came to the realization that what Archimedes was doing with areas and what Newton and Leibniz were doing with slopes are actually connected to each other. Mind blowing. So we'll look at that. But it all starts with the idea of a limit. So, I started you off with this walking example where I had 8, 4, 2, 1, half. If you keep cutting it in half, eventually when I say how far am I walking when I walk half, it's going to get so close to 0 that we basically can say that it's 0. And so we say as n goes to infinity, Tn goes to 0. I did this experiment with my, we never found out, I did this experiment with, you can see how your R values are half with my grade 11s. And I said, what happens when you plug in 10? And then your calculator, your graphing calculator has like an e to the minus 5 because it has scientific notation. And then we went to 100 and it's like e to the 62. And then we went on our calculators and did 10,000 and our calculator had already given up. It's like too many zeros. I can't even put it into scientific notation for you. Your calculator gives up and just says 0. It's not true. Right? If you do 0.5 to the 10,000, it is not equal to 0. But it's so close to 0 that your calculator's already given up. So we say that that's approaching a limit. as n gets bigger and bigger, our terms go to 0. And that's why when I add up 8 plus 4 plus 2 plus 1/2, I'm approaching the wall, which means the sum of all of those approaches 16. And that's the limit of the sum. Okay? We use this word arbitrarily close. Because what do you mean by you're arbitrarily close? Well, think of something that's really, really close and not touching. Okay, like this, I'm even closer than that. We'll cut that in half. Oh, even like so close that you can't fit anything in between them, but they're still not touching. Kind of close. How's that even possible? If they're not touching, you should be able to fit something in between them, but if you fit something in between them, I say cut that in half and we can get closer than that. Like, oh. So when we say arbitrarily close, you're basically there. And when we're talking about limits, if we say the limit is 2, you're like, okay, you're basically at 2. You're so close to 2 that we could say that you're at 2, but you're not exactly there. So we did this, and I talked about this already. So if we added these all up, we would get to 16. So we would say the limit of Sn is equal to 16 as n goes to infinity. And of course, in grade 11 pre-calculus, we even wrote S infinity like this. And you had a formula for S infinity as you're going forward. Ooh, I got some decimal math for you to think about coming up. Okay. So if it approaches a limit, some important definitions, you can highlight this if you like. We call it convergent. And this is our notation that we start to write. We write LIM for limit. Underneath the LIM, we write what it's getting, what n is getting close to, or whatever variable you have. So the limit as n goes to infinity of term n is going to equal 0. The limit as n goes to infinity for the sum would equal 16. If the limit does not exist, and it's not convergent, we call it divergent. If I always walk double what I used to walk, how far will I walk? If I keep doing that forever, it'll just keep getting bigger and bigger and bigger and bigger. And that would be divergent. So when something is divergent, the limit does not exist. Here's a sequence. I start with point 2, then I have point 2, and then I have point 2, 2, 2, and then point 2, 2, 2, 2, 2. Eventually I'll get pizza. And then it'll go on forever. What does that get closer and closer to, but never get to? The answer would be, right? The answer would be point 2 repeated, which is the same as 2 nights. You don't need to see the other boxes, they're just they're just fractions. But you're getting closer and closer to 2 nights. Did you know that point 2 repeated was 2 nights? This sequence, can you see that it never gets to point 2 repeated? Even if you check the billionth one. The billionth one has a billion 2s. But it's not repeated yet. No matter which one you look in the sequence, it never keeps going forever because the sequence stops at a number. But we would say the limit of this sequence as n goes to infinity would be 0.2 repeated. And we're going to look at limits of functions. And some of our limits are going to be super, super easy to figure out. I'll start off with a function you already know. Let's make f of x x squared, because you know what that looks like. That's this graph right here. And if I ask this question, here's 1, here's 2. Would you agree that you have the point 1, comma 1, and you have on this 2, comma 4? This is your standard parabola. And the question is, what is the limit as x gets really, really close to 2? And the answer is really simple. The answer is going to be 4. Like, if I plug in 1.999, I would be right there, wouldn't I? I'd be really close to 2. I'd probably get 3.999 as an answer. And if I plugged in something really, really close to 2 but bigger, like if I come from this direction and I come from that direction, as I get closer to x equals 2 from this direction and get closer to x equals 2 from that direction, I'm going to get really close to 4. It's so simple, it's obvious. And if you have a graph like this one, which is continuous, means you can draw it without lifting your pen, then you can just plug in the answer to find the limit. Like the limit as x goes to 1 will be 1. I can just plug in the answer. But graphically, I can see that if I come from both sides, it gets closer and closer to 4. If I come from the left side, my graph is increasing, getting closer to 4. If I come from the right side, it's decreasing, getting closer to 4. And we would say the limit is equal to 4. So limits of functions like x squared are really quite boring. Because basically it's like, just plug in the value. What's the limit as x gets close to 3? It's going to be 9. It's not a hard question. Because you can actually plug in 3. So if I know what happens when I plug in 3, then it's going to be easy to find the limit. But limits get interesting when you can't plug in the number. And you've done some questions like this before as well. Okay, so we did this question. I guess I left space for it, but we did it already. It's 4. If we actually did a table of values of this question, can you see from the table of values that if you didn't plug in 2, 2's right there. Can you see that you're getting closer and closer to 4? Ooh, spelling mistake. Do you see it? I hate the form spelling mistake in my notes. Because it never gets underlined in red pen. Is it still wrong on yours? Oh. The next one's a little bit interesting. X squared minus 1 over x minus 1. Unlike this previous one that we just did, you can't plug in 1. We have a problem. If I type in values, okay, I want to show you some calculator stuff that you might find interesting. So I'm going to open up my calculator here. And I'm going to type in x squared minus 1 over x minus 1. And in your graphing calculator, you can draw the graph, which is nice. You can also get a table of values. So if I go second table, it shows me a table of values, but I have an error at 1. That's the limit I want to find. So I want to get close to 1 on my graphing calculator. Right now, I feel like it's jumping by ones is not super close. So something you can do on your calculator is above the window button, there's this table set. So if I go second table set, it's like right now I'm starting at 0. I'm jumping by 1. Maybe I want to jump by 0.1. Okay. So now I go to my table and I'm jumping by 0.1s. Ooh. I'm feeling like I have a guess now. Do you see that it's going 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, error, 2.1? I feel like maybe it's getting close to 2. So I'm going to go back to my table set, and I'm going to get even closer. I'm going to go 0.01, and maybe I'll start 0.01, 0.01, and I'm going to start at 0.9. Go to my table. Ooh, okay, I'm going to look at it, it's 1.99, error, 2.01. I'm starting to feel better about it being 2, even though that is an error there. So I'm going to go back to my notes. I'm going to say that I did this table of values. And I feel that with my table of values, as I got closer and closer, I feel that it's equal to 2. But we can see this even better from our graph. Do you remember how to graph this from grade 12? This is a rational function with a non-permissible value. When you have a non-permissible value, it's either an asymptote or a hole. How do you determine that? Well, you would factor. So if I factor the top, it's x plus 1, x minus 1. I'm like, yay, my x minus 1's cancel out. And I get a hole. Where is that hole? Well, after it cancels out, the line you get is just y equals x plus 1. If I plug in 1 into x plus 1, I get a hole at 1 comma 2. And that hole that you graphed in grade 12, that's your limit in calculus. Because if I go towards it in this direction and I go towards it in this direction, I never touch that hole. That hole is non-permissible, it's not allowed. But I can get as close to the hole as possible. Because everything else is included. Only 2 is not included. So if you draw a graph and you find out where the hole is, that will be the limit as it gets close to that value. Even though you're not allowed to plug it in. If you're allowed to plug it in, usually that's your limit. Usually. I can think of crazy exceptions, and you know that the AP Calculus will like to play with your brain to find crazy exceptions. But for the most part, anything else on this line, like if you wanted to find out, what happens when x approaches 2? It's going to be 3. 3 over 1, 3. That's the limit. Sure enough, as x gets close to 2 right here, both directions, it gets close to 3. Guaranteed, because that point is included. Graphically, we're going to talk about this graph is called discontinuous because it has a hole in it. If a graph has no holes and you can draw it all at one, we call it continuous. Sometimes graphs are going to have different pieces. We did some piecewise functions. We're going to do some more of those today as well. All right, here is our next example. This is a piecewise function. This graph is equal to 1 for x bigger than or equal to 0, and equal to -1 for x less than 0. If we draw this, it's two straight lines. We have an open circle on one part and a closed circle on the other. You had some like this on your take-home quiz, where you had to draw different pieces for different domains. Okay. So what happens when you go from one side? It's always -1. And from the other side, it's always +1. Check this out. This is interesting. F of 0 is equal to 1. Because that point is on my graph. I have the point 0, 1. I don't have the point 0, -1 because of the hole. So we have the point that f of 0 is 1. But in calculus, if we say, what happens when we get close to 0 for f of x? This does not exist. Even though f of 0 is 1. So this is an example where I can plug in the value and get an answer. But the limit doesn't exist because from the one side, I'm getting close to -1. But from the other side, I'm getting close to 1. And for the limit to exist, it has to go to the same number from both sides. So in mathematics here, we would say that the limit doesn't exist because it depends on your perspective. The people that are traveling on this road are like, they've been checking values. They're pretty good at patterns. They're like, did you check -0.2? Yeah, what'd you get? Oh, -1. Did you check -0.1? Yeah, what'd you get? -1. They have now been working at this for years. They've checked 8 million values coming from the left-hand side. They've got -1 each time. Someone says, hey, what do you think is going to happen if we get close to 0? And everybody on that side is going to say, it's going to get close to -1. But everybody on the right-hand side is saying, we've also done a million calculations. Everything we've calculated says we're getting closer to positive 1. So we have a problem. From the left, it's -1. From the right, it's positive 1. We're going to say that this limit doesn't exist. We're going to have notation even. We're going to have a notation that looks like this. And that exists. If you put a little negative above the number, that means you're coming from the left side. We're going to put a little positive beside the number, you're going to come from the right side. So we're going to get notation that says you only come from one side, then the limit exists. But sometimes the notation, in order for the actual limit to exist at a number, it has to be the same from the left side and the right side. So these are our one-sided limits. So here's a piecewise graph. We call these graphs that are discontinuous. We have names for each discontinuity. Sometimes we have a hole. This one is called a jump discontinuity because if you want to go from the green graph to the blue graph, you actually have to literally jump from one point to the other and skip a whole bunch of numbers. I'm not going to do the table of values. You don't need to write that down. I know you can graph a parabola and a line. So it's good enough to draw these points. Maybe you would label your hole here at 1, 1 and your starting of this one at 1, 3. Those look like important points on my graph. So if we want to look at the left side, we put that little negative there. So the limit as x goes to 1 from the negative side, which means you're traveling along the green graph. And if I had a point, I'll draw a big, I know what I'm happy face. All right. If I'm on the green graph and I'm traveling along the green graph from the left, getting closer and closer to x equals 1, I'm going to get really close to the y value of 1. And so we would say from the left side, as x gets close to 1 from the left side, I would be on the green graph. And so my y value would get close to 1. But if I did the right-hand side, that means my happy face is starting on the blue graph, and now I'm going to 1 from the right. So, whoops. Whoa. Oh my goodness, come on, there we go. We're getting closer and closer and closer and closer. And as I get really close to 1 on this side, my right-hand limit will be 3, because then I would be on the blue graph. And our actual limit does not exist because the left-hand limit and the right-hand limit are different. What is that? Added Mean Girls on there.
She says, like in the math competition, like if the limit never approaches anything, it doesn't exist.
Okay. I have seen Mean Girls, but not enough that I could quote it. But I like that some of you got the connection. There we go. So the ordinary limit, which is sometimes called a two-sided limit, because an ordinary limit is the left limit and the right limit combined. It doesn't exist because it is approaching different values from left to right. So in mathematical writing, we say this. If the left limit doesn't equal the right limit, then the actual limit does not exist. But if the left limit equals the right limit, equals some number L, then the actual limit also equals that number L. So graphically, if our graph is nice and you draw it without lifting your pen, which we'll say is continuous, then all of our limits are nice and easy. When limits get a little bit tricky is when we have holes in our graph, asymptotes in our graph, jumps in our graph, then we start to have some problems. So again, if I want to find the limit, if it exists, of x approaching to 2 of f of x, the graph is really helpful. Although some of you won't want to draw graphs because drawing graphs is annoying. But for right now, we'll draw the graph. I draw the green graph, which is x squared, on my green graph. Because 2 is the important point, I would have 2 comma 4. And can you see on the green one, that would be an open circle because 2 is not included in its domain. And on the blue graph, I would have 2 comma 4, and it would be on that one. So this graph has 2 pieces, but the pieces are perfectly connected because the whole of the one graph gets filled in by the other graph. We would say that this graph is continuous. You could draw it completely without lifting your pen. I'm not going to, you don't have to, I think you can do the table of values. You could figure out how to graph these. Are we good at graphing these? I don't want you to waste your time drawing them. But then we could say that the limit from the right side is 4. The limit from the left side is also 4. And therefore, the actual limit exists and is 4. The graph shows it nicely. So does it make sense in a piecewise graph? If there's a jump, it won't exist. If there's an asymptote and one side goes up one way and one side goes down the other way, it's not going to exist. If you have an asymptote and they both go up towards the asymptote, you will see some textbooks say it doesn't exist, and some textbooks say, well, technically they're both going to positive infinity. So some textbooks will write the limit as positive infinity, and some will write does not exist. So we'll see that in some of the examples that we do. So having the ability to draw graphs in your head, very helpful. Okay? This one, would I need to find it in my head? No, because I could do this algebra, the left side and the right side, separately, pretty easily, and see that they're the same, and then say that it works. I can see that it works, the limit works for my graph. I can also see that the limit works from the algebra. And some of you will like the algebra better because you don't like drawing graphs. What about the next one? Five x plus 5 is a straight line. X cubed minus 1 is your x cubed graph. Move down 1. Drawing a picture. And then label what happens at 2. 1 is at 2 comma 7. 1 is at 2 comma 15. We have a jump discontinuity here. And because of that, the limit's not going to exist. Algebraically, you could look at the left limit and the right limit. You can see the answers from the graph. You can also see the answers from the equations. We can do one more. This one's a little bit tricky. It's got an absolute value in there. This is not something that you've done before, so we might need to go to a table of values to see what's happening. 0 is undefined. When you plug in all of these positive numbers, it's always 1. But when you plug in negative numbers, it's always negative 1. In fact, we drew this graph earlier. When we had a piecewise graph of this. But now we have open circles on both sides. So here, the limit as x goes to 0 of f of x does not exist. Because if you come from the left side, it goes to -1. If you come from the right side, it goes to +1. They're not the same. And we're done. For today.